Okay, so looking here, we have question 2, and it says a ball is thrown straight up. When the ball reaches the highest point, what happens? So you have this velocity here. It starts, large velocity going up, so that's why it's going up, because you threw it up. It'll go up, it gets smaller, reaches zero at the top, it gets bigger as it comes back down. It's obviously pointing up when we go up, and down when we're coming down. So it says when the ball reaches the highest point, well, your velocity is going to be 0 because it's changing direction, so we know this has to be true. And then it also asks about its acceleration. Well, the acceleration is always caused by the Earth, so the acceleration is the acceleration of gravity. So the acceleration is always down towards the center of the Earth. So the acceleration cannot be 0. And the velocity is 0 at the top. So that's it for the first question there. Well, not first question, but first one we're looking at. So number 3, it says, okay, we've got a graph shown below with the instantaneous acceleration at 5 seconds. So if you're looking at this graph, get a quick sketch here. It goes up, over, and down, and this is velocity times time. So whenever we're looking at a velocity time graph, we know that the slope is acceleration, and the area under the curve is displacement. So if you don't know those things, you need to review your notes on why that is. But since this is a velocity time graph, that's what this is. And then it asks for the instantaneous acceleration at 5 seconds. So 5 seconds, looks like this occurs at 4, and this is 6. That's 4. So 5 seconds is going to be somewhere on this line here. So instantaneous acceleration, we want to find the slope of line tangent. Well, the line tangent at 5 seconds is just going to be the same as the slope of this entire line. So we can pick any 2 points on this line to find our acceleration. So I'm going to probably pick at 4 and 6 because those are pretty easy. So at 4 we have the point, looks like 20, right? 20, and then at 6 the y is 0. So to find the acceleration, we do the change in y or the change in x, or the change in velocity or the change in time. So we do final minus initial. So our final velocity is 0, initial is 20, and this is 6 over 4. So always final minus initial. Right? Final minus initial, final minus initial. So I'm going to get negative 20 over 2. So that would be negative 10 for our slope, which would be our instantaneous acceleration at that point. Alright, so that was number 3. So let's look at 4, got it right. Let's look at 5. So 5, it says, what must you do to non-perpendicular vectors before you can use the Pythagorean theorem to calculate the resultant of the vectors? Okay, so there's several things here. Several things you have to know. So let's go through this. So it says, what must you do to non-perpendicular vectors before you can use the use Pythagorean theorem to calculate the resultant? So let's start with perpendicular vector. So if you had a perpendicular vector here, and this one's perpendicular, so it's 90 degrees. So to calculate the magnitude of our result, remember the resultant's right here. To find the magnitude of the resultant, we use Pythagorean theorem. And you could say a squared plus b squared equals c squared, and we say r squared for the resultant. And then, if we're finding the angle, that would be a different step. So it's saying, okay, well, if you want to do this, what do you have to do with vectors that are not perpendicular? So if we had, the first vector like this, and the second one like that or something, how do we add these two together? Well, the first thing that we talked about in class is to do this using the same steps. you're going to have to take each thing here and break it into its components, right? And so we talked about using a sine to find the y component and cosine to find the x. Remember, it's not always that, it depends on what you're looking at. And so we can use that for both of these. So once you find your components, like you'd have a component here and a component there, this thing is essentially, you know, if we're breaking it along standard coordinate system here, you don't really have to break that one. So you got this first one go this way, and you have the second one come this way. And then from here, you go up. So you'd have this tiny little triangle here that's like a little bit of up and a little bit of over. And then we can use Pythagorean theorem here to find this resultant. So that's all the question's saying is you need to break them into the non-perpendicular vectors into components. That way you can easily add them. All right, so, excuse me. Number 6, got that one right. 7 is right, 8, 9, 10, good. That's good. Okay, so now 11 here, it says a vector remains unchanged. So remember a vector, you know, like we have drawn here, has a magnitude and a direction. You can take this vector and you can move it anywhere you want, right? But the magnitude, the size of the vector should remain the same, and the direction should remain the same. So you can move it anywhere you want, but it can only be moved parallel to its original direction. Because if you did something like moving it perpendicular, like if it's like this, then I move it, you know, like that way. Well, that's obviously not going to be the same direction. So you don't want to change the size, that's obvious. But you also have to be careful not to change the direction. So the only way you can be sure of that is to move it parallel, right? So each one would look nice and parallel. All right. So here, we have a car that starts 318 meters north of the town square, and then it has this average velocity of this. How far in meters will the car be in 21 minutes? So if you can imagine, let's say north is up. Let's say this is the town square, and the car starts 318 meters north. And then it's going to, well, continue north. Okay, so let's write down what we know, what we're looking for. So if the town square is our origin, 0 kind of gives that to us. Our car starts, we could say x. It initially starts 318 meters north of the origin. So remember, all vectors have magnitude and direction. Although direction doesn't seem like it's going to play too much into this since it's all north. And it says then we have an average velocity. There's average velocity, x direction. 30 meters per second, also north. And then how far in meters will the car be in 21 minutes? So the last thing it gives us is the time of 21 minutes. And then it says how far will it get? So we're looking for a final position. So since this is in meters, and this is in meters and seconds, and this is in minutes, I know that these two don't have the same units. These are fine. So I want to convert minutes to seconds, so we know that there are, in 1 minute, there are 60 seconds. So to find how many seconds are in 21 minutes, I just need to multiply 60 times 21, and we'll get 1260 seconds, because those will cancel. So now I wish to find the distance. So we have our average velocity equation. Average velocity in the x direction is delta x over delta t. Well, delta t is 2160, so I guess I should be a little more specific here, because that's the time interval we're looking at. And we want to find x. So the first thing we have to do is multiply this by delta t, and we get average velocity in the x direction times delta t equals delta x. And so remember, delta x is always final minus initial. So final is what we're looking for, and we know the initial. So we're going to move that over to the other side. So I'm going to pull this out. I'm going to add x naught to both sides. That'll cancel. So that'll give me average velocity in the x direction times the time interval. I can read all that. Plus x naught equals x. And so I gave you another version of this, which you could just jump straight to if you remember that one. So average velocity is 30 meters per second. And we'll do that times 1260 seconds. And then we'll add the 318 there at the end to get x. So 30 times 1260 plus 318 gives us 118 meters. And that's our answer. Alright, so it looks like 13 was right, 14 was right. So 16. Which of the following pairs of graphs shows the distance traveled versus time and the speed versus time for an object uniformly accelerated from rest? So we're looking at a distance versus time graph and a velocity versus time graph. Well, let's start with velocity, or as it says there, speed versus time. So if it says speed, that means we don't have to consider the direction. So if we're thinking about a velocity or speed versus time graph, it says we want uniform acceleration. So remember, the slope on this type of graph is going to be the acceleration, and the displacement on this graph, well, the displacement is the area under the curve. I should have wrote area first, but whatever. So if we have a uniform acceleration, what that means is that the acceleration is not going to change. So if the acceleration does not change, it would have a nice constant line here on this graph. Now, if we had a flat line like this, that means a constant acceleration, but it would be 0. We can't have 0 because it says for an object uniformly accelerated, that's a uniform acceleration, but from rest, which indicates that it's going to change speed. So this can't happen. So we can have a straight line up or a straight line down, something like that, but it's got to be a straight line. So if we're looking at our options here, the first option is straight and the last option is straight. Okay? So those are only 2 options there. So we've already eliminated B and C, answer choices on this essentially. So we have this one that curves like this for distance and one that curves like this for distance. So here, there's different ways to get at it. I think the easiest would be just looking at, we're thinking about what's happening. Okay, so we've got 2 that are going up, so let's mark those out. So if we know our velocity graph has to do this, well, what would our position graph do? Well, for a uniform acceleration, it's going to curve. And so you'll notice our 2 options, one curves up and one curves down. So this one has a negative curve to it, and this one has a positive curve. So essentially here, if our speed is constantly increasing, then our distance should constantly be increasing too. So we want a constantly increasing distance. So we cover a little bit of distance, and then more, and then more, and then more to match this graph. Essentially, if you want the other curve, the curve down, you'd have to have the velocity going diagonally down in that case, which, essentially these graphs match and these graphs don't. So both this distance and this distance represent a constant or a uniform acceleration, but it doesn't match with what's happening with their speed. Okay, number 17. An automobile travels 25 kilometers west, then 35 kilometers south. The displacement of the car is 10 kilometers at... Oh, that's your answer. Okay. So, it's just asking for the magnitude and direction of the displacement. So, if we put this here and say, okay, this is our origin, right? It says it travels 25 kilometers west. Remember, north, south, west, and east, right? So it's going to go 25 kilometers west, so 25, and then 35 kilometers south, 25. And what is the displacement of the car? So displacement has a magnitude and a direction. So magnitude, we can use Pythagorean theorem, right? R squared equals a squared plus b squared. And it looks like that was the issue here. So we would do 25 squared plus 35 squared, and we'll get an answer. So don't forget your square roots. So do 25 squared plus 35 squared. That gives us 1850. But remember, that's going to be r squared, and we don't want r squared, so you'd have to take a square root to get our answer. So r would just be the square root of that 1850. So it's about 43.01 kilometers. Okay. And then to find the direction, well, that's to be this angle here. So to find the angle, it's going to be tangent inverse. Remember, that will be opposite over adjacent. So in this case, this side would be opposite, and this side would be adjacent. So I'm going to do tangent inverse of 35 over 25. That will give me an angle. So it gives me an angle of 54 point, I guess we just round it to 5 degrees. Okay. So then remember, we're always going to report our angle from positive x. So positive x is over here. So we're going to go all the way over here. So through quadrant 1, through quadrant 2, to somewhere in quadrant 3. So we know this is our angle from the x-axis in quadrant 3. So to get from here to here, that's 180 degrees. So we have to add 180 degrees to that to get our total angle. So 180 plus our angle gives us 234.5. And so that agrees with our answer. Alright, let's see, what else we got? We got 18, 19 is an answer. Okay, so 19 says, the cliff divers of Acapulco push off horizontally from rock platforms about 37.6 meters above the water, but they must clear rocky outcrops at the water level that extends out into the water about 7 meters from the base of the cliff, directly underneath their launch point. How long are they in the air? So if you draw this cliff, so they're just going to jump off the cliff into the water. And it says they push off horizontally, so they just jump straight out. So, you know, they run and jump or whatever. But the key there being is they come off horizontally. So this launch angle is 0. And so all your velocity is in the x direction. Alright, so it gives us a height and a distance. So the height is 37.6. 37.6. And the distance is not a very good picture because it says the distance is only 7 meters. Okay, so we want to figure out how long they are in the air. Well, that's time. based on the stuff it gives you, we don't need this at all to find time. We just need the vertical stuff. And so we can use the second kinematic equation. That's the y equals y naught plus v naught yt plus 1/2 ayt squared. So this is set up for vertical, and we know our initial velocity is only going to be the x, so our y velocity is 0. And remember, if we have that 0 condition and we're solving for time, we can just jump straight to the 2 times our height over the acceleration of gravity. So we can do the square root of 2 times 37.6 over 10 meters per second squared. That's meters. And that'll just give us our time directly. It's obviously from solving this equation for time. So I say square root of 2 times 37.6 divided by 10. And you get a time of 2.74 seconds. That's it. So if you're not sure how I got this, just remember to solve this guy for time and you get the same answer. Because that's 0, and if we say that it started from here, your initial height would be 0. Okay, so 20. It says the car rolls off the cliff's edge and hits the water. 6 seconds later, if the car strikes the water 106 meters from the base of the cliff, how fast was the car going when it left the cliff? So again, this is another horizontal projectile. It gives you the range as 106 meters and gives you the time. So time equals 6 seconds. And so this is your range. This is kind of like delta x. So we got time, we got range, and it says how fast. Well, if it drives off horizontally, again, this is all in the x direction. There's no angle there. So remember, your average velocity, your initial velocity, your final velocity, all velocities in the x direction are the same because there's no acceleration. And then we have our formula delta x over delta t. And it's just asking you to find Vx. Well, we know delta x is 106. And we know delta t is 6. So we just do 106 divided by 6. So it is about 17 2/3 or 17.67 meters per second. Alright. That was pretty easy. 21. A jumper in the long jump goes in the jump with a speed of 12.5 meters per second at an angle of 10.3 degrees above the horizontal. If it lands at the same height, how far does the jumper jump? Okay, so it's going to go up, and it's going to come back down. And it gives us this initial velocity and the launch angle. And it asks for the time, no, the distance. So we want to find delta x in this case. So I'm going to find this total displacement here. Okay. So the first thing you should do is take your velocity and break it into its components. Got 12.5. And it gives us an angle here, so this will be Vx and Vy. I'll put knots on, so Vy naught, Vx naught. This angle's 10.3 degrees, so we're going to use sine and cosine. So sine, so V naught y is your hypotenuse times sine theta. V naught x is hypotenuse times cosine theta. So the hypotenuse is 12.5 times sine 10.3, and this one is going to be 12.5 again times the cosine of 10.3. So V naught x is 5 times cosine of 10.3. So 12.3 meters per second. And then now we do the same thing but with sine. We get 2 meters per second. Okay. So we split that, and if we're trying to figure out how far, again, we know delta x is related to our x velocity, delta x over delta t. So in order to find delta x, we have to multiply both sides by delta t. So the delta x equals vx, vx naught or whatever, it's all the same, in x, times delta t. Okay, well I've got v naught x, I can use that, but I don't have the time. So in order to find the time, I need to use our y. So we know some stuff about y. We know, for instance, that it's going to go up and going to come back down. We know our velocity in the y direction at the top point is 0. And it's just asking for time. So since this is a parabola, I would use the first kinematic equation, dy equals v naught y plus at. And we know that the acceleration of gravity is -10, it's going down. And we're trying to solve for time. And we want the time of the whole thing. And in order to find that, well, we need v naught y. Well, we got that. This is the 2.2 we found earlier. Oh, what did I write? 2.3. This is the 2.2 earlier, but we need to find our final velocity. Well, we know the velocity is going to go up and come back down. So we know this is positive, and we know the acceleration is going to be negative. In order to solve this equation, we need a final velocity. Well, we could go find it from our third equation, but since this is a parabola and it's symmetrical, it will go, what goes up must come down. So since it's landing at the same height here and here, we know that the final velocity would be the same as the initial, but negative. So it's the same velocity as our initial because it's at the same height, but it's going to be a negative velocity because it's going the opposite direction. So now I have enough information to solve. So I'm going to subtract 2.2 from both sides. Now to cancel. So here we get -4.4 equals -10t. Divide both sides by -10. And we get t equals 0.44 seconds. So now we can plug that time in here with our x velocity, which is 12.3. And do times 0.44. So delta x is 5.4 meters. Thereabouts. Alright, so we got that. So looks like 22 was good, 23 was good. So we got 2 more left here. So 24 says okay. Plane drops a rubber raft and survives as a shipwreck. The plane is flying this height with the speed of that. The raft lands next to the survivors, ignoring air resistance. How far away from the shipwreck was the plane when the raft was dropped? So it's another horizontal projectile problem. So we know all of our velocity at this point is in the x, and the vy at that point would be 0. And it gives us our vx. It says it's 107 meters per second. And then the raft lands next to the survivors, so there's some people down here, right? So the question is, how far away, delta x, is the, from the shipwreck was the plane when the raft was dropped. So we're looking for delta x, okay. And it gives us an additional thing here, the height. So I could say the height is 1086 meters. So if we're talking in terms of y, if we put our origin here, it will fall down 1086 meters. So if we're going down negative, I could say that its initial position is 0, and it falls down to a final position of negative 1086 meters. And so in order to figure out how far away, well, we already know Vx. And so Vx is delta x over delta t. And again, if I'm finding delta x, this equation becomes Vx times t, just like on the previous problem. But again, I know Vx, but I don't know t. I have to find it. So in order to find t, I use the height. And since I have my distance and a time, or I have a distance and I'm looking for time, that's our second kinematic equation again. So we have y equals y naught plus v naught t plus 1/2 ay t squared. So this is 0 and this is 0. So once again, we can find the time using our square root of 2h over g. Well, g is 10, but let's stick to one thing at a time here. G. So this becomes 2 times 1086 over 10. So the time ends up being that. And if you don't believe me, put negative 10 in here, negative 1086, solve for t, and you'll get the same thing. 2 times 1086 divided by 10. So we get 14.73 seconds. So now we can use this guy here, so delta x is Vx, which is 107, times 14.73. So delta x is 1576.93. So, yeah. So you get a slightly different answer if you use 9.8 or 10, but that's why we got the margin of error set. All right. The final question here says you have a base jumper who's going to jump off a cliff, and he's going to make things complicated for us by jumping up at some angle and then coming down. So, we need to take our initial velocity here and split it into x and y. So 9.5 meters per second. And we got this angle here, 5.8. It's a pretty small angle. And so we can find v naught y and v naught x. We find those just like we found them before using sine and cosine. So I'm going to do 9.5 times sine of 5.8. And then we use cosine for x, so 9.5 cosine of 5.8. So 1.5 times the sine. So it's a small angle, so we should expect a small y. We do get a 9.6 meters per second, or 0.96 meters per second, I should say. So now we'll do the cosine here. And we get 9.45. Now, it also gives us the cliff's height, this height here, of 968 meters. So if we want to put, say, our origin here, it's going to fall down. And we could say that we have our initial height of 0 and our final height of negative 968 meters, because it falls down that far. And as always, here at the top of our parabola, Vy is 0, because there's a change direction at that point. So we're looking for how far. So that would be from here to there. Again, we're going to look for delta x. So as we've seen in previous problems, delta x can be found from doing Vx times our time. So we have Vx, we just need the time. Okay, so let's find time. So if we're going straight for time here, if we use our second kinematic equation, so this is the last problem, so it's going to be difficult, but if we use our kinematics equation, y equals y naught plus v naught t plus 1/2 ay t squared. So this is negative 968. Y naught 0. It looks very similar to what we've done, but now we have a Vy. So this is 0.96 times t plus 1/2 times negative 10 t squared. Okay. So now we can't just use our fancy simplified formula. So we got two options. We can solve this using the quadratic equation, or we could go back and use the third equation to find the velocity, and then use that velocity in the first equation to solve for time. Since I'm here, I'm just going to use the quadratic formula. So remember, the quadratic equation is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in order to get this, we have to get the right form here, so I'm going to add 968 to both sides, because you've got to be 0 equals in order to use quadratic equation. So this will be negative 5, so I'm going to write it, like a normal thing. So I'm going to write the squared term first. I got negative 5 t squared, so that comes over here, plus 0.96 t, and then plus 968. So this will be our A, B, and C. So I think I did all that right? Starts from here, falls down, negative. Okay, so now we plug in. Yeah, you can just type this in your calculator, whatever, but I'll try to go slow here for the video. So B is in the middle, plus or minus b squared, so 0.96 squared minus 4 times negative 5 times 168, square root of that whole thing, and then divide by 2a, so 2 times negative 5. Okay, so 0.96. Remember, you get plus or minus for any square root. I should have pointed that out earlier. So you'll get 2 here, but obviously the other number here would be negative, so that one's not relevant. So let's do 0.96 squared. You get 0.92. 4 times 5 times 968 gives you 19,360. And negative 4 times negative 5 will give you a positive. And then 2 times negative 5 would be negative 10. Okay, so this is not going to contribute much here. So we'll add the 0.92 to that. And so we get, 19,360.92. Okay, so we got to take a square root. So x equals 0.96 plus or minus, so we take a square root of that number. We get 139.14 over negative 10. Okay, so we're going to get a plus and a minus, so we'll do plus straight across here, and we'll do minus down here. So if we add 139.4 plus negative 0.96, we'll get 138.2 divided by negative 10. So then that will give us negative 13.8 seconds. So that would be this time over here. We don't want that time. So let's try the negative one. So you have negative 139.14 minus 0.96. So we get negative 140.1 over negative 10. Well, it's obviously going to give us 14.01 seconds. So that would be down here. That would be this part. So that's the time we want. So we've eliminated this one. So now we're going to use this time back over here with this guy. And we get delta x equals the x velocity, 9.45, times 14.01. And we get a range of 132 that's a 4 meters. And that's it. All right. Hopefully that was helpful.